let's move on to hydride chemistry. Now, hydrides are similar to Grignards in that they produce something minus. Grignards produce R groups minus. Hydrides produce H minus. Hydride literally means H minus. H with a lone pair and a negative charge. There are two reagents you have to know. Sodium borohydride. Sodium borohydride and lithium aluminum hydride. Now, if you want to draw the Lewis structure, here it is. There's sodium borohydride. And here's lithium aluminum hydride. Very similar in structure. There you go. Now, both of these can be considered a source of H minus. Now, believe it or not, these things are going to react just like Grignards do. So if you know the mechanism for a Grignard reaction, you know the mechanism for a hydride reaction because they basically react exactly the same. There are differences, but they do react essentially the same. There you go. So that's a source of H minus. But now why would we have two? If they basically react the same or in essence react the same, why would we have two different reagents? Well, first of all, not every reagent will work with every molecule in the world. That just doesn't work that way. Normally, they'll in general do the same things, but sometimes there's some nuances. First thing you have to understand is sodium borohydride is good for ketones and aldehydes only. It will work with ketones and aldehydes only. I don't know if you guys can hear that. It started to rain here. We're going to plow through the rain, though. Ketones and aldehydes only. Now, lithium aluminum hydride will reduce everything. Now, when I say everything, I mean ketones, aldehydes, esters, acid chlorides, amides, nitriles, I believe, too. What am I thinking? I'm missing one. Pretty much everything. It pretty much reduces everything down to the alcohol. So let's see how these things work. Let's say we have ourselves a ketone. So we have, say, acetone. And there's a little bit of sodium borohydride. Okay? And that's going to give us the corresponding alcohol. Now, first things first, you do that first, then you put a little bit of, work up it up in water, a little bit of acidic water. These reactions work very, very nicely. So remember, sodium borohydride is going to act as if it were H minus. It's not. The mechanism of this reaction is much more complicated than this, what I'm about to show you. But this is the accepted drawn mechanism for sodium borohydride. What's actually occurring in the flask is a lot more complicated, so don't think it's quite this simple. So the hydride, just like a Grignard, attacks the carbonyl carbon, kicks up the pi bond, just like we've already seen. Same play, different actors. That's all this is. All right, so that's going to give me there you go. And now anion there. Throw in some protons. There you go. And that product will be, let's try it over here. A little more room over here. There you go. It'll be the secondary alcohol. So all we did really, if you want to just break it down to what we've actually done, we've taken a carbonyl and we've added a hydrogen to it using a hydride. And we formed an alcohol from that. In fact, one of the more common ways of making alcohols, because it's so much easier than Grignards, is to use a ketone or an aldehyde and reduce it. Now, sometimes you can't. Sometimes you have to use a Grignard because you want to add a carbon as well. Because Grignards are awesome because you can add carbon groups. Hydrides, you can only add hydrogen. Okay. In this hydride, the sodium borohydride is typically very, very well behaved and very simple to run. Grignards and a lithium aluminum hydride require special conditions. They require special attention because they can't have any water. A couple of examples of sodium borohydride reduction. You can try the mechanism out at home if you like. And you get the alcohol, no big deal. Here's another example. You can try the mechanism at home if you like. It's pretty straightforward. Just look at the example I gave you. It's exactly the same. It's just a different looking ketone or aldehyde. Oops. So ketones, again, will give you secondary alcohol. And aldehydes will give you primary alcohols. All right, so that's how you do it, and that's how it works. So again, sodium borohydride will reduce, in a mechanism extraordinarily similar to the Grignard, will reduce ketones and aldehydes to get the corresponding primary or secondary alcohol. That's how they work. Now, lithium aluminum hydride will reduce ketones and aldehydes all day long. Not a problem. Lithium aluminum hydride can definitely do that reaction. But they can go one step further and reduce esters as well as acid chlorides and a bunch of other stuff. Okay, so let's just take a look at lithium aluminum hydride reducing an ester. Now you're going to see this is extraordinarily similar to when a Grignard added to an ester. In fact, it's the same bloody mechanism. The only difference is instead of an R group, it's hydride. That's the only difference in the mechanism. So let's draw a very simple run-of-the-mill ester. Now, sodium borohydride will not do this. It's not strong enough. It's not reactive enough. I'll say it that way. Well, lithium aluminum hydride sure is. Okay, so lithium aluminum hydride is a source of H-. The mechanism is going to be the same. Here it comes. Attacks the carbonyl carbon, kicks up the pi bond. By this time in the lectures, you should have no problem with this. This is okay. This is what Grignards and hydrides do. No problem. Now remember, the Grignard's mechanism, when reacting with an ester, you're going to see huge similarities. In fact, you're going to see exactly the same mechanism, only it's a hydride. That's the only difference. Here comes the lone pair. Kicks off the O-. Now, that's the same thing you saw with a Grignard reacting with an ester. Same thing. Nothing is really new here. It's just different players playing the same game. Okay, another equivalent of hydride. Attacks the aldehyde. There you go. So far, I hope you guys are starting to recognize that nothing's really all that different here. It's basically the same idea over and over again. There we go. And now, throw in the protons. Source of hydronium. Probably dilute HCl. Oops, change the color back to black. There you go. And that will give you the primary alcohol. The black hydrogens come from the hydride, and the blue hydrogen comes from the proton source, the hydronium. And there you go. So that is the mechanism. Now remember. Sodium borohydride cannot do this. Sodium borohydride can only react with aldehydes and ketones. Lithium aluminum hydride can react with esters, acids, acid chlorides, everything else. It can reduce everything. Lithium aluminum hydride is a very reactive reducing agent. Sodium borohydride, much milder. Another way to make alcohols from carbonyls is to do a direct reduction of the carbonyl using hydrogen and Raney nickel. You don't have to know the mechanism of this reaction, just know the conditions, H2 and what's known as Raney nickel. And that will give you the alcohol. It'll basically add hydrogen across the pi bond to give you that. Now, Raney nickel is just a hydrogen-rich nickel source, so it's a nickel metal that's been pumped full of hydrogen. So there's lots of hydrogen in there, and that's how it reacts. Now, this is not a very common method because this method will also reduce down a bunch of other stuff. It'll also reduce double bonds, triple bonds, probably nitriles as well. It'll damage a lot of other things in a molecule. So it's generally speaking not employed very often, but it does exist. So I want you to know about it. So now, guys, with that, this is the very last thing we're going to talk about in this course. So you've made it to the end. Congratulations. I'm very proud of you for sticking with it for this long. Very, very tough course. So props to you. Shout out to you guys for being freaking crazy awesome. Thank you guys for sticking with it. And then with that, for the final time in this course, I want to wish you all good luck and good chemistry. We will see you soon. Bye for now.